Why, hello everybody. Let's start with section 14.4, which deals with motion in space, velocity, and acceleration. So the first thing I want to do is define a few vectors for you. The first one is the position vector, which you already have had, r of t. We're assuming right now that we're in three-dimensional space, but you also could be in two-dimensional, in which case your vector would just have an x component and a y component, and both of them would be written in terms of t. We can take the derivative of r and get what's called r prime of t, and in this section I'm going to call that my velocity vector. All right, the direction of that vector is showing me the direction that the motion is going, because we all know that r prime of t is tangent to the curve. All right, and its length tells you how fast you're going. And if we take the derivative of the velocity vector, just like you do in physics class, you get what's called acceleration. So acceleration is equal to the derivative of the velocity vector, but if I differentiate both sides here, I'm going to get r double prime of t. And again, you take derivatives of vectors term by term, which you're quite comfortable with. And lastly, speed. Speed is the magnitude of the velocity vector, and the velocity vector is r prime of t. And we also could represent that as ds dt, because that's how fast you're moving along the curve, how fast your arc length is changing with respect to time. Okay, so that's pretty easy. So without further ado, let's go on and do an example. Suppose I have this three-dimensional vector, r of t equal to sine t, comma t squared, comma cosine of t. I want to figure out the velocity, the acceleration, and in this course, when we use the word velocity and when we use the word acceleration, it's implicit that we're talking about a vector. These are vector quantities. Speed, on the other hand, is a number. It's a scalar. It's the magnitude of your velocity vector. All right, so to find my velocity vector, piece of cake, it's just r prime of t. And so I would differentiate this term by term. Derivative of sine is cosine. Derivative of t squared is 2t. Derivative of cosine t is minus sine t. And that's my velocity vector. Now, if they want me to evaluate my velocity vector at t equals 0, if I want to evaluate that vector at t equals 0, what we're doing, and I should have put an arrow above that because it is a vector. The velocity vector evaluated at 0 would be cosine of 0. 2 times 0 is 0, minus sine of 0. And I guess you're understanding how important trigonometry is in this course. And we get cosine of 0 is 1, 0, and sine of 0 is 0. So the velocity vector evaluated at t equals 0 is the vector 1, 0, 0. In addition, we could want to figure out what v prime of t is. And what that is my acceleration vector. And again, all we're going to do is differentiate term by term. So the derivative of cosine is minus sine. Derivative of 2t is t. And derivative of sine t is cosine t. And if I want to know what is my acceleration vector evaluated at 0, it's going to be minus the sine of 0, which is 0. 2 minus cosine of 0 would be negative 1. Now your book asks you to draw these three-dimensional position vectors, and they're okay. And then they want you to draw the velocity vector and the acceleration vector right on the curve, and that's really difficult to do a good job. I did not assign those for homework. Okay, we'll do it in 2D, but we're not going to do it in 3D. Now lastly, they want me to find the speed of the particle. Now formally to find your speed, notice we write speed as just v with no arrow above it. All right, that's equal to the magnitude of your velocity vector. This would equal the square root of the x component squared of the velocity plus the y component squared plus the z component squared. And I think most of us agree that since cosine squared plus sine squared is 1, this is equal to 1 plus 4t squared. So if we wanted to know what's the speed of the object when t equals 0, we just plug a 0 in here and we get 1 plus 4 times 0, or 1. So our velocity at t equals 0 is 1. Not hard, very easy. What makes it hard? The differentiation. Okay, that if you're going to mess up, it's because you forgot how to differentiate. All right, now I told you in 2D, it's not so hard to draw the velocity, the acceleration, and the curve all in one picture. So let's do this example right here. Find the velocity, acceleration, and speed. And we're going to do that just like we did before, but this is just 2D in this case, so we just have two components. But lastly, they want us to sketch the path of the particle and draw the velocity and acceleration vectors at t equals -2. So first I'm just going to get my velocity vector. V of t is equal to, derivative of 2 minus t is a -1, derivative of t squared is 2t. And my acceleration vector is derivative of -1 is 0, derivative of 2t is 2. All right, now in particular, if I'm concerned about where is my object at t equals 2, I plug a 2 up in here, and I get my object at t equals 2 is 2 minus 2, which is 0, and 2 squared is 4. My velocity vector at 2 is going to be -1, comma, and we're plugging a 2 up here, so 2 times 2 is 4. And lastly, my acceleration vector is equal to, plugging in a t equals 2, and I'm plugging in a t equals -2. So, did I mess up? I messed up, people, and nobody hollered. Just letting Mrs. Strocko go right along. T equals -2 is what they asked us to plug in, and Mrs. Strocko unfortunately plugged in t equals 2. So instead of rewinding the tape and fixing it, let's just do it again. So r of -2, where is my position at -2? It's going to be 2 minus a -2, which is 4, and a -2 squared, which is 4. So we're going to be at the point 4, 4. My velocity at -2 is going to have an x component of -1, but 2 times a -2 is a -4, and my acceleration at -2 will just stay at 0, 2. Okay, now they want me to sketch the path of the particle and then draw these three vectors. Well, in fact, they just want me to draw the velocity and the acceleration vectors at the point that corresponds to t equals -2. So first of all, before I sketch my curve, I'm looking here and I'm saying, what does the curve look like whose vector function is given as r of t equals 2 minus t comma t squared? Well, notice your x-coordinate is equal to 2 minus t, and your y-coordinate is given as t squared. So what I'm going to do is I'm going to take my x equation and I'm going to solve for t. So I'm going to add a t to the left and subtract an x on the right. I just solve for t. So I have t equals 2 minus x, so if y is equal to t squared, y would be 2 minus x squared, and 2 minus x squared is exactly as x minus 2 squared. So the path, the curve that this particle is going to be moving along in two-dimensional space could be described as y equals x minus 2 squared. So what I'm going to do is I'm going to graph y equals x minus 2 squared in two-dimensional space. Okay, I'll just fold that there so I can keep that. Move this down a little bit so maybe you can see it a little bit better. All right, and let's see, to graph that, I think I'll take a pencil first just to do my points. When x is 0, y is a -2 squared, which gives me 4. 1, 2, 3, 4. When x is 1, I'm 1 minus 2, which is 1, or -1 squared gives me 1. When x is 2, we're at 0. If I put in a -1 here, -1 minus 2 is a -3 squared, gives me 9. So that's 4, 5, 6, 7, 8, 9. And I know from symmetry of a parabola, I'm also going to have a point there. All right, so my parabola looks like this. Okay? Yes?
Is it 2 minus x?
Well, 2 minus x and x minus 2 are the same, because if you notice, if I took this, I could factor out a -1. You okay with me? Inside the parentheses, I factor out a -1. And notice, if you take a -1 and square it, you end up with a positive. Oops. So this graph and this graph are one and the same. Okay? Just like a minus a squared and an a squared are one and the same. Okay? So it's the same parabola. But good question. I'm sure somebody at home. Now, they want me to correspond to the point that corresponds to r of negative 2. r of negative 2 is the point that you get by 2 minus a negative 2, which gave me 4. And negative 2 squared is 4. So r of negative 2 is the point 4, 4. 1, 2, 3, 4, right here. Okay? Now, we figured out a few minutes ago that, let me fold this back so you can see it. We figured out the velocity at t equals negative 2. The velocity we figured out was the vector negative 1, negative 4. So my particle is right here at t equals negative 2, but the velocity vector has an x component of negative 1 and a y component of negative 4. I want to draw that velocity vector at the point where the particle is at t equals negative 2. So to draw that vector, I'm going to start here, but I'm giving an x component of negative 1 and a y component of negative 4. 1, 2, 3, 4. And this is v of negative 2. Do you notice how beautiful this is? It's tangent to the curve. It's showing me at that point the object's going this way. The direction shows you which way you're going. The magnitude shows you how fast you're going. Now the acceleration vector has a magnitude of 0 for the x component and 2 for the y component. So I want to draw the acceleration vector in the direction that it's pointing. Its x is 0, its y is 2. So my acceleration vector at negative 2 is going straight up because it's x. I'm drawing it from the point where the point is on the curve. Its x component is 0, its y is going up. Pretty cool, huh? So your velocity vector points you in the direction of motion. Its length shows you how fast you're going. Okay, we're doing all right? All right, now, what could I put on the test for people to mess up? I could give you one in which you have to know how to differentiate things easier than algebra expressions, right? Algebraic expressions. So what we want to look here is we have r of t is equal to e to the 2t, natural log of t squared, cosine of 2t. And just to review things that people mess up on is if you have y equals e to the u, y prime is e to the u times the derivative of u. If you have y equals the natural log of u, your y prime is 1 over u, but don't forget to multiply by the derivative of u. And lastly, if you have, I don't care what the trig function is, let's just make it be cosine in this case, your y prime derivative of cosine, yes, is minus sine, but most of my students, a lot of my students, forget to multiply by the derivative of what's inside. So we just have to remember how to do that. Also, it's sort of nice with logarithms to remember, when you have a log of x to a power, can you simplify that? Sure, you can bring down your power and do this, can't you? Okay, so first of all, before I even differentiate, I'm looking at r, and I see I have an e to the 2t, but why not bring that 2 out front? If you didn't see to do that, you'll get the same answer that I'm going to get as long as you simplify. So they want me to get the velocity. My velocity, r prime, is, all we have to do is differentiate term by term. So derivative of e to the 2t is e to the 2t times the derivative of 2t, which is 2. Derivative of 2 times log t is 2 times 1 over t, but the derivative of t is 1, so you don't need that thing I talked about. And derivative of cosine is minus sine of 2t times the derivative of 2t, which is 2. And that's my v. All right, now to get my acceleration, I need to differentiate again. Well, I have a constant 2 times e to the 2t, so it's going to be 2 times e to the 2t times 2, right? Because the derivative of 2t is 2, so I'll have a 4 here. The derivative of 2 times 1 over t, I think most of you realize you could write that as 2 over t or 2t to the minus 1. So if I call that y, if I want to differentiate it, I get minus 2t to the negative 2, which is a negative 2 over t squared, right? Simple algebra 1, not algebra 1, calculus 1 thing. So this is going to be a negative 2 over t squared. And we have a negative 2 times derivative of sine 2t is cosine 2t times the derivative of what's inside, which is 2. So I've got to take that 2 and multiply it times the negative 2 and get a negative 4. So this is my acceleration vector. That's my velocity vector. Lastly, they wanted me to get the speed. Speed is the magnitude of the velocity vector. Notice they're not asking me to get the speed at any particular time, so I'm going to write the speed in terms of time. It's going to be the magnitude of this vector. So to find the magnitude of a vector, you just take the square root of the x component squared plus the y component squared plus the z component squared, which gives me square root of, now, some of us struggled with this the other day, so let's do this one right here. To square this, 2 squared is 4, but we've got to take e to the 2t and square it. And when you have a power to a power, right, what do you do with the powers? You multiply them. So it would be 4e to the 4t. I'm using the fact that like x to the a to the b is x to the a b. So this one squared is 4e to the 4t, plus you square that, you're going to get 4 over t squared, plus you square this, you're going to get 4 sine squared 2t. They did not give us any particular time to evaluate this for, so life is good, we're done. If you want to know the speed at t equals 0, plug in t equals 0. If you want to know the speed when time is 10, plug in 10. If you want to know the speed when time was pi, plug in pi. Okay, any questions? We're doing okay? All right, moving right along. Let's do this one. This is a fun one. They give me my acceleration is minus 10k. And on the basis that acceleration is minus 10k, they want us to find r of t and v of t. And they're giving us some initial conditions. I always put this on the test, by the way, so when you look at the practice test, you'll see one of these. They tell me my velocity when t is 0 is I plus j minus k, and my position at t equals 0 is 2i plus 3j. All right, now we're going to be using those initial conditions momentarily. But first of all, notice I have the acceleration with respect to time. I prefer to write it as the vector 0, 0, negative 10, because its z component is a negative 10 and its x and its y's are 0. And remember, acceleration is the derivative of velocity. So if I want to find out what velocity is, I can integrate both sides. But it's an indefinite integral, so I'm going to get that stinking plus c each time. So my velocity is going to be, now what we need to do, we have to integrate, and I'll write these right below here. Well, in fact, I can write it out. We got to integrate 0 dt. We've got to integrate 0 dt. You go, how boring, Mrs. Strocko. And then we have to integrate a negative 10 dt. So my velocity is, now what's the integral of 0? It's 0. But with every indefinite integral, we get plus c. So I'm not going to write 0 plus c. I'm going to just write c. But since I have three different components, I'm going to call him c1. When I integrate the next one, it's going to be 0 plus c2. And the third one is going to be negative 10t plus some other possible constant. Now before I continue here, I have to find out C1, C2, C3. Because they told me to find C. I have not found C yet. How am I going to find out C1, C2, C3? By using the initial conditions they gave me. Okay, now I'm just going to fold this over so we can line it up so you can see. But we're told that v of 0 is the vector I, j, k. So if I evaluate v of 0, which right now we have is C1, C2, minus 10t plus c3. If I plug in a 0 here, I get c1, c2. Minus 10 times 0 is 0, plus c3. But I'm told v of 0 is the vector whose components are 1, 1, minus 1. So that tells me c1 is 1, c2 is 1, and c3 is a negative 1. So now that I know what C1, C2, and C3 are, I can write what V is. V is equal to C1, which is 1, comma, C2, which is 1, comma, C3 is negative 10t minus 1. Notice if you plug in v of 0, what do you get? V of 0 is 1, 1, negative 1. If you differentiate v with respect to t, you should get your acceleration. What do you get? 0, 0, negative 10. I know I'm right. So this is my first answer. This is my v. Now they want me to find out r. Well, I know r prime is equal to v. So r is going to be integrate again. But this time we'll have more constants. So let's see, if I integrate 1, you see you're integrating 1 with respect to time, integrate 1 with respect to time, and lastly integrate minus 10t minus 1 with respect to time. We get r is equal to, the integral of 1 is t plus some possible constant. The integral of 1 is t plus some different constant. And the integral of minus 10t is what? Minus 5t squared minus t plus some third constant. Okay, so I integrate it term by term. Now we are told further that r of 0 is the vector 2, 3. So let's see, r of 0 is, plug a 0 in for t, I get d1. Put a 0 in for t, I get d2. Plug a 0 in for t, I get d3. But I'm told this is the vector 2i plus 3j. So that's the vector 2, 3, 0. So two vectors are equal if and only if their components are equal. So I know now d1 is 2, d2 is 3, and d3 is 0. So taking these and plugging them back up here, my final answer for r of t is t plus d1, so it's t plus 2, t plus d1 is t plus 2, t plus d2 is 3, and minus 5t squared minus t plus d3 is 0, and I'm finished. Okay. Any questions? We doing all right? Okay. Moving right along. Okay, and I'm checking there. It looks good. Looks like we did well. All right, let's do another one. In this one, they want us to determine r of t and v of t, given that a of t is blah, 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 and they tell me v of 0 and r of 0. And then lastly, they ask me to use a computer to graph the path of the particle so we can see what it looks like. Okay, same thing all over again. We have v prime is equal to t, t squared, cosine of 2t. To save some time, integrating is pretty simple. The integral of t is 1/2 t squared plus some constant. The integral of t squared is 1/3 t cubed plus some other constant. And lastly, we might want to do this on the side. We've got to figure out what's the integral of cosine of 2t dt. If you think it's just minus sine 2t, notice how wrong you are, because the derivative of this should be what's inside, right? Let's differentiate and see. If I differentiate minus, well, in fact, it's plus. If I differentiate sine 2t, I get cosine 2t times 2, don't I? So I need to have a over 2 to compensate. So when I differentiate this, I indeed get what's inside there. So the integral of cosine 2t is sine 2t over 2. So this is going to be sine 2t over 2 plus c3. Okay, now we know, though, that v of 0 is c1, c2, sine of 0 is 0, so that will be c3, is equal to the vector 1, 0, 1. So c1 is 1, c2 is 0, and c3 is 1. So now I can tell you what v is. V is equal to the vector 1/2 t squared plus 1, 1/3 t cubed plus 0, 1/2 sine of 2t plus 1. And this is my v. Okay, everybody doing okay there? All right, now r prime is equal to v. So to figure out what r is, all we have to do is integrate again. Integrating 1/2 each time. Remember though, you're doing an indefinite integral, you got to go plus a new constant. I use c's first and then d's. So let's see, if I integrate t squared as t cubed times a third, so that'll give me 1/6 plus t plus some new constant. Let's see, if this is t to the fourth and you divide by fourth, you'll get a 12 t to the fourth plus some other constant. And this is going to be minus cosine 2t times an additional 1/2, that's going to give you 1/4, right? Because the derivative of cosine 2t is minus sine 2t times 2. Then we need to have plus t plus d3. So therefore, let's see what r of 0 is. R of 0 is going to be 0, 0, it's d1, 0, d2. And be careful here, because a lot of times students always think that with this one, notice when you put in a 0 here, though, cosine of 0 is 1. So I have minus 1/4 plus d3. And they had r of 0, looking back, was 0, 1, 0. So this tells me d1 definitely is 0. d2 is 1. But minus 1/4 plus d3 is 0. So it looks like d3 is 1/4. So what is my r here? My r is going to be 1/6 t cubed plus t plus 0, 1/12 t to the fourth plus d2, which is plus 1, comma, minus 1/4 cosine of 2t, I'm just reading off here, plus t plus d3, which is 1/4. And this is my final answer for r. Okay. Any questions? Doing all right? Okay, not hard, not hard. And we did, what, 2 of them? So I think we should be very comfortable with doing it. Okay, moving right along. Now we're going to do a little bit of, oh, they wanted us to draw it. I apologize. So let's go back and do that on Maple. They wanted us to use the computer to graph the path of the particle. So what we have to put in is r of t. That's what we have to put in to see what it looks like. So just remembering how to do that. First I need to turn my calculator on. Okay, there we go. Let me make this a little bit bigger for you to see. Remember to do a 3D graph, I have to load with plots. WITH, parentheses, PLOTS. All right. And notice when I load with plots, there's one that I'm going to use right there called space curve. So what we're going to do, let's scroll this down a little bit. We're going to, down here, type space curve, SPACE, CURVE, parentheses, brackets, brackets. You use brackets in Maple when order is important. And X, there's a difference between when you change your X, Y, and Z coordinates. So I have 1/6 times t cubed, t raised to the third, plus t, comma, 1/12, which is 1 divided by 12, times t to the fourth, t raised to the fourth, plus 1, comma, minus 1/4 times cosine. Notice when you do your trig, it's always parentheses around your angle. Cosine of 2t, parentheses, plus t, plus 1/4, close your brackets, and then you have to tell it what t ranges from. I'm thinking I'm going to let t range from, since it's cosine of 2t, why don't we let it go from 0 to 2 pi? Close parentheses. Let's hit enter. Okay. It's starting to graph it. Let's click on the graph. I'm going to pick that to be on the outside, and if I move it around a little bit, I can get a little better idea of what the curve looks like. Okay, this is the x-axis here, this is the y-axis, there's the z-axis, and we could play, adding, get all different kinds of ways of looking at it. Okay, pretty neat to be able to see what that curve looks like in 3-dimensional space. Okay, well, let's move on and do paper and pencil stuff. All right, why does anybody care about these wonderful derivatives? Physicists love this stuff. In order to apply this stuff to physics, we have to know Newton's second law. Newton's second law says if F, now F is the net force acting on an object. You have a net force acting on an object. It says that net force acting on an object is equal to the magnitude of your mass times your acceleration. Now, in the British system, we're going to use, for acceleration, feet per second squared. Okay, and for our mass, which we really don't have to worry about, we'll use pounds. Well, it's not even pounds, so we're not even going to even use that because we're going to use acceleration. Now, in the metric system, we will use for our acceleration meters per second squared. Okay, force unit in the British is pounds. In the metric system, force unit is newtons. Now, we're only going to do one example, one. Okay, but we're going to do multiple ways that you can look at it. So what I'm looking at is, I have an object right here on the ground. Now, when you do physics problems, you have to decide where you're going to put, now it's only a two-dimensional problem. I'm not doing a 3D problem, all right? 2D. I have an object right here, and I'm going to choose to draw my x-axis and my y-axis right where the object is at t equals 0. So I'm making the location of the object, not an r of 0 to equal the vector 0, 0, because my location at t equals 0 is right there. Now, many of you have played baseball, right? You've thrown something up into the air and you've watched it fall down, and you know what its trajectory looks like. It looks like a parabola. It goes up and it comes down. All right, now the law of physics, or the force that's acting on this object, is gravity, pulling down. All right, and gravity tells us, or our formula says, the force due to gravity is always downward. So if it's downward, what component it is? It's the j component, right? And that force is equal to minus mg times j. Minus mg times j. That's the force of gravity. The reason this ball goes up and then it comes down is gravity's pulling it down, and finally gravity wins out and it hits the ground. Now, what I wanted to figure out first of all is, I'm saying that I'm sending this thing up with a velocity v naught. All right, that's the velocity vector, all right? And the angle that we projected this thing into the air is alpha. All right, so let's just draw that little picture right here instead. Here's my x and my y-axis. V naught, that's my, by the way, v sub 0 means your velocity at t equals 0. That's what that little 0 means, your velocity at t equals 0. And this is angle alpha. Now, we're going to let the magnitude of v naught be our speed. All right, so v naught is the magnitude of that vector, because we said speed was your magnitude of your velocity vector. So the length of this vector is v naught. Now, what I want to figure out is what's the x component and the y component of this velocity vector. Well, I think most of you would agree, if this is my hypotenuse, the side opposite the acute angle, opposite goes with sine, so it's going to be v naught sine of alpha. And the adjacent is going to be v naught cosine alpha. So by what do I mean by this v sub 0 x? It means what's my x component of the velocity vector when t is 0? Initial speed in the x direction. What's my y component in the y direction initially? Well, we just figured out by looking at this picture that my x component is v naught cosine alpha, and my y component is v naught sine alpha. So if I wanted to represent my velocity vector at t equals 0, which means v of 0, what's my velocity at t equals 0? That would be the vector whose x component is v naught cosine alpha, and its y component is v naught sine alpha. We all comfortable with that? Much to do about nothing, if you ask me. We're doing okay. All right? Now, what I'm doing in the next couple minutes, I want you to sit back and follow, but don't frantically copy. All right? First of all, I'm starting out with mass times acceleration equals force. All right? Then I look at that and I say, but acceleration is dv dt, right? It's v prime. So I have m times dv dt equals, and we said the force due to gravity, in physics they tell me it's minus mg times j. M is your mass. If we're in the metric system, it's kilograms. Does anybody know what g is? What is g? G is your acceleration due to gravity. This only works if you're at the Earth's surface. It does not work if you're on the moon or on Venus. All right, it's totally dependent on the mass of the Earth. Acceleration due to gravity is 9.8 meters per second squared if you're in the metric system. If you're in the British system, it's 32.2 feet per second squared. Okay, now the reason I didn't put the minus, some of you are like, Mrs. Minus, it's down, Mrs. Strocko, is because we wrote the force as minus mg, because it's coming downward. Now you notice the m's cancel. So I have dv dt is equal to minus g times j, j being my x component. All right? Okay, now taking that, let's look here what we have. dv dt means, what is this talking about, dv dt? You have a velocity vector. It has an x component and it has a y component, right? So when you're differentiating it, you're differentiating the x component and you're differentiating the y component, right? And we're saying the derivative of this vector v, that's its x, that's its y, is equal to, and minus g we can write as 0 comma minus g, because the y component is minus g. All right, so moving along. Now, if two vectors are equal, this x component equals that x component, and this y component equals this y component. So what I'm going to do is I'm going to break it up into two separate equations. Over here, I'm setting dv, the derivative of the x component of the velocity vector with respect to time, is equal to 0. And if I integrated both sides, which I will, I get Vx is equal to 0 plus some constant, which I'll call C1. But do you remember a few minutes ago? If I plug in a 0 here, let's plug a 0 in here. What is my velocity when t is 0? It's C1, but we found out it was V naught cosine alpha. So C1 is V naught cosine alpha. So I have a representation for my x component. So in other words, people, what this is saying is when an object's thrown up as a projectile, when it goes up into the air and down, its component in the x direction is constant. If you throw a ball up into the air and look down, and the sun, the sun's way up here, and you just look at its shadow moving along, how fast its x component is moving, it's going to be going at a constant speed. And what is that speed? That speed will be V naught cosine alpha. Now I'm going to do the same thing for the y component. And here what we have is the derivative of the y component of v with respect to time is equal to minus g. Integrating both sides, I get minus gt plus maybe some constant c2. But remember, the velocity component in the y direction evaluated at 0 would be minus g times 0 plus c2. But a few minutes ago, we evaluated initially at t equals 0, your y component was v naught sine alpha. So c2 is v naught sine alpha, and this is how we can represent v sub y. Now notice, people, your velocity vector is your x component comma your y component. So my x component is v naught cosine alpha, and my y component is minus gt plus v naught sine alpha. That's my velocity vector. Now, unfortunately, we're going to do it again. All right, we're going to do it again. Here I have my velocity vector, which I just copied what I had written there in red. But what is v of t? It's r prime of t, right? And what is r? R, you have an x component, a y component, right? So when you're saying r prime of t, it means differentiate the x component with respect to t, the y component with respect to t equals this. So what are we going to do now? We're going to set this equal to this, and this equal to this. Okay, and when we do that, let's look. On the left-hand side, I got dx dt is equal to v naught cosine alpha. Okay, What are we going to do? Integrate. Integrate both sides. Now notice V naught cosine alpha is a constant. V naught was the initial speed the thing was thrown up at. That's not going to change. And alpha was the angle that it was projected at. So when I integrate, I get V naught cosine alpha t plus C1. But at t equals 0, plugging that in, I get all of this. Now no, this is cosine of alpha times t. So I get 0 plus C1. So I say, at t equals 0, what is my x-coordinate? Well, remember, at t equals 0, where was the object? Right there at the origin. And so your x-coordinate was 0. And so therefore C1 is 0. And this is how I would represent what my x-coordinate is at time t. Now taking the exact same, let's look at this. The second half, we have dy dt is equal to this. And if I take dy dt, set it equal to this, integrate both sides, I get this. But then we say, oh, y of 0 was 0, and that equals 0. This is sine alpha times t. 0 plus c2. So what do we know about? c2 is 0, and y is this. Okay? So now it's time to take notes. All right? What we have just derived is the following. If you have an object at the origin and you launch it up into the air and it goes up and it goes down, you have a velocity vector which I'm going to write as v sub x of t, comma v sub y of t. V sub x is equal to this, v sub y is equal to this. This is saying in the x direction I'm going this fast, in the y direction I'm going this fast. In addition, you might want to say, where is the projectile? Where is it right now at time t? It will have an x component and a y component. What is its position? We just figured out the x coordinate of where the object is given by this equation, and the y coordinate is given by this equation. Absolutely, people, you are allowed to bring this cheat sheet with you to your test. I don't expect you to go through the whole derivation that I did. But it wasn't that hard. If you look at it, all I did was integrate, find the constants, integrate, find the constants. That's all I did. And we said if you integrate acceleration, that's v prime, you get v. If you integrate v, which is r prime, you get r. That's all I did, nothing deep. But now let's apply this stuff. Any questions? First thing I want to do is I want to figure out what's this distance. Now notice, we can make life really interesting and we can move things around. The problem we're doing is the object is being launched at ground level, okay? And it's coming back to ground level. So I would love to find out what we call the range. Can I have a formula for how far that object has been launched? Not hard, not hard at all. What can you tell? Now notice, when you hit the ground, you know something about its position. I want to find the x-coordinate. I already know the y-coordinate. What's the y-coordinate?
0.
It's 0. So this equation right here that's giving me my y-coordinate must be 0. All right, so if I take that equation right there, y of t equals v naught sine alpha t minus gt squared, when I hit the ground, well, I already have it written there, y is 0. So I have 0 equals v naught sine alpha t minus 1/2 gt squared. Now notice, I'm going to factor out a t. 0 equals t times v naught sine alpha minus 1/2 gt. All right, now to solve this, if two things multiply to give you 0, either this is 0, well duh, when t is 0, people. When t is 0, that's when it got launched. Yeah, it was at ground level, that was nothing new to me, all right? But the other t is when it hits the ground, right? So let's set this piece equal to 0. Okay, now let's see. I could add a 1/2 gt to both sides. Is it okay if I multiply through by 2? Question there? got to multiply through by 2. And then to solve for t, now why did I want to solve for t? This is telling me the time I hit the ground. The time I hit the ground. Everybody with me? I said, what I did is I took this equation and I factored it. I factored out a t. So it's either this is 0 or this is 0. You could set t equal to 0, but that's when it's launched. Yeah, it's on the ground at that time. This equal to 0 is going to give me when it hits the ground. I solved that for t. This gives me time hits ground. I don't want to know the time that it hits the ground, even though that was nice if somebody asked that. I want to know what this distance is. Well, if I know the time that it hits the ground, which I'm copying is 2v naught sine alpha over g, I can take that time, plug it into x, and find out what my x coordinate is at time t. You all with me? So if I do that, I get my x, when it hits the ground, is v naught cosine alpha times t, and t is 2v naught sine alpha over g. That's what the x coordinate when it hits the ground. Now cleaning this up a little bit, I get 2 v naught squared cosine alpha sine alpha over g. And if you notice, I have it right here on the top of the sheet that I'm just writing on. That's what I got there for the range, but I like this one so much better. Because what did they do? They took this, and you take the v naught squared out, and you go 2 sine alpha cosine alpha over g, right? And what is 2 sine alpha cosine alpha? Sine 2 alpha. So this is a wonderful formula that gives you, if you throw something into the air, and you want to know how far is it going to go before it hits the ground, that's its range. Do we want to put that on our cheat sheet? I think so. It'll make life a little bit easier. Okay? So this is a neat little thing. We just figured out how we can describe motion using vectors. All right, now the force we used was gravity. I mean, if you take physics with this stuff, you can do a whole bunch more. But let's look at a couple of examples. First thing I want to do is a projectile is fired with an initial speed of 300 meters per second and an angle of elevation of 40 degrees. 40 degrees. So what's happening here? It's being launched at 300 meters per second, and the angle is 40. So v naught is 300 meters per second, and my angle of elevation, alpha, is 40 degrees. And for part A, they say find the range of the projectile. You say, oh, good, Mrs. Strocko, you just derived that. You want to find the range? You want to find this distance from it goes up till it hits? That's the range. You just derived, Mrs. Strocko. It's right here. It's v naught squared sine of 2 alpha over g. What's my g? What is my g? If you're in the metrics, it's 9.8, and the unit is meters per second squared, even though you don't have to put that in. Copying my formula for range right here, I have my range is equal to v naught squared sine of 2 alpha over g, and plugging that in, my range is going to be 300 squared. The sine of 2 times 40 is 80 degrees divided by 9.8. Okay? I already did that. No sense turning on the calculator. And I got 9044. And it's going to be in meters because it's a distance. Notice my distance unit is meters because I'm doing meters per second. Okay? We could turn on the calculator, but that just takes another couple seconds. Okay, we doing okay? We might turn it on for another one. Next one they want me to do is figure out, so we did this one, they want me to figure out the maximum height. Now the way you're going to do these problems is, you want this picture with you, all right? And you have to ask yourself, all right, Mrs. Strocko's asking for maximum height in here. Now right now with this problem, I know v naught was 300 meters per second, and I also know my alpha was 40 degrees. I'm just copying that down again. And my g is 9.8. They want to know what is the maximum height, and thirdly, they want to know the speed at impact. What's my maximum height? Well, let's look at this. Where is the maximum height? right here. What do you know up there? What do you know up there? Well, look, from here to here, your y-coordinate is rising, so dy dt is positive. From here to here, your y-coordinate is decreasing, so dy dt is negative. So if dy dt is positive here and dy dt is negative here, what do you think dy dt is at the top? It's going to be 0. And that's your velocity in the y direction, right? dy dt is your velocity in the y direction. So at the top, your velocity in the y direction is 0. So I think what I would do was I would say, oh, this is 0. My velocity in the y direction at the top is 0. So minus gt plus v naught sine alpha is 0. Well, why not plug in what we know? G is 9.8. V naught was 300. Alpha was 40. It looks to me that t is going to be 300 sine 40 over 9.8. Now, what's that going to give me, though? That's going to give me the time that I'm at the top. Everybody with me? Let's take the calculator out for this one. Taking the calculator out for this one. I just want to find out what my time is, turning it on. Let's see. Oh, you guys can see. I just can't. So I'm just going to hit F1 8 to clear this screen. And let's hit clear. All right. I'm going to go. Now I'm going to hit my mode to make sure I'm in degrees. And looking along there, it's radians. So coming down here, I better change that to degrees and hit enter. Enter, escape. Okay. Okay. Let me take sine of 30 just to make sure I have it in degree mode. Gives me 1/2, which is correct. All right. So my time is 300 times the sine of 40 degrees divided by 9.8. And so my time is approximately 19.677. 19.677 seconds. But we want to know the maximum height. So going back and looking at here, what's going to give me the height? The y-coordinate, right? When you plot that point, you go over x up y. It's going to be, what's my y-coordinate at that point? So I'm going to take my y equation, which is v naught times sine alpha t minus 1/2 gt squared. And I'm going to plug in this 19.677. Now, since I'm feeling a little bit lazy right now, my v naught was 300. My angle was 40 degrees. And I could type that, but I don't want to. This is going to be 9.8 times t squared. What I'm going to do on the calculator, just to make life a little bit easier for me, take out my trusty calculator. I'm going to tell it to take that number and store it for t. I'm going to hit enter. Okay, so now t is stored as 19.67. All right, and then I'm going to type 300 times sine of 40 times t, because t has the 19.67, minus 1/2 is 0.5 times 9.8 times t, and unfortunately on this calculator to do squared you have to go raised to the second, and hit enter. All right, and I got what, 1897? About 1897 meters. Okay, all right, and good, that's what I have on my answer sheet, so that's good. All right, let's do the third one. So we did this one. The speed at impact. The speed at impact. They want to know the speed that it reaches here. How fast is it when it reaches there? So they're asking for the magnitude of the velocity vector. But in order to get the velocity vector, I have to know the, what do I have to know? The time. Any suggestions how you could do that? Multiple ways. If I go back and look at my notes, we looked at this thing going up and coming down. When you hit the ground, what did we say we know when we hit the ground? We know y is equal to 0, right? If we plugged in, in fact, let's take y equals 0 right here. So when I hit the ground, I know y equals 0, so I have v naught, which is 300, sine alpha, which is sine 40 degrees, times t, minus 1/2 times 9.8, which is g, t squared, equals 0. So I have 300 times the sine of 40 degrees times t minus 4.9 t squared equals 0. Well, let's see, if we factor out a t here, we get t times 300 sine 40 degrees minus 4.9 t equals 0. And I can either set, if these two things multiply together give me 0, I can set t in equal to 0. Well, duh, t equals 0 is when you start the problem. Or I can take 300 sine 40 minus 4.9t and set it equal to 0. And that looks to me like t is going to be 300 sine 40 divided by 4.9. Now notice, I think I'll get what that number is. I think I'll take the calculator out and do that. All right, taking it out, let's see what I get. I'm going to go turn it on. I'm going 300 times sine of 40, close parentheses, and divide by 4.9. And I'm getting, oh, missing parentheses. So I hit escape, and what did I forget? Where's my parentheses? Oh, yes. I can see that. I didn't close it on sine of 40. Let's do that. It's sine of 40 parentheses divided by 4.9. Okay, and I get 39. Now notice, people, notice something here. Let me go up here. This was the time that it was at the top, all right? That was the time that it was at the top. Notice if I multiply it by 2, I get the time that it hit the ground. Well, that makes sense. It takes an equal amount of time to go up as it does to come down. So taking that 30, I'm going to take that 39.35. I'm going to store him as t. Okay, so now t is 39.93. Now, 39.93, right? That is the time it hits the ground. Unfortunately, people, they didn't ask when does it hit the ground. They asked what was the speed when it hits the ground. What is the speed that it hits the ground? So we have to find out what v is. So taking our sheet out, we have the time it hits the ground is 39.93. To get v, we need to find out what is v at 39.93. So taking this out again, it's not hard. I need to get my two components. My x component's a piece of cake. In fact, I'm going to move him down here. It's going to be v naught, which was 300. Alpha was 40. My y component is minus g, which is 9.8, times t, plus v naught, which is 300, times the sine of 40. You all with me? Okay? This is the x and the y components. Now notice I didn't put down what t is because I stored that in my calculator, so I can just type t, even though we could type 39.93. So coming back here, let's get our two x and y components. To get our two x and y components using the calculator, I'm going to go, what's 300 times the cosine of 40? And I get, give it to me as a decimal, please. I get 229.81. To get the y component, I'm going to go negative 9.8. Now I stored the time as t, so I'm just going to go times t plus 300, and I'm going to put a decimal point in the 300 because in the TI-92, if you put a decimal, it gives your answer as a decimal, times sine of 40. And I get negative 192.84. Now that makes sense, because at this point, when the object is coming down like this, it has a positive x component, but a negative y, right, because it's coming down. Now to get the speed, the magnitude of that vector is going to be the square root of the x component squared plus the y component squared. And popping that into the calculator, I'm going to go square root of parentheses 229.81 squared plus 192.84 squared, close parentheses, enter. And it looks like I got 299.99. Let's round that off to 300. And that will be meters per second. Okay, so with these problems, you have to look at it and you got to say, 9 times out of 10, if they want to know what's the maximum height, you got to say, how do I get the time at the top? If they want to know what's the speed at impact, how do I get the time at the impact? We have a couple more I'd like to just talk about how you would go about doing it. Save these. We did this one, which was a doozy. A ball is thrown at an angle of 30 degrees to the ground. It hits the ground 100 meters away. Determine the ball's initial velocity. Well, first of all, it's thrown up at an angle of 30 degrees, so I know my alpha is 30 degrees. It hits the ground 100 meters away. What does that equal? Aha! My range is 100 meters. And they want us to figure out the initial speed. Well, we could derive a whole bunch of stuff, but I derived a formula for the range for you people. This one I like the best. V naught squared sine 2 alpha over g equals my range. So copying that, range equals V naught squared sine of 2 alpha over g. And let's just plug and chug. They told me my range was 100. My V naught squared, I don't know. My alpha is 30, so I'm going to take sine of 60. And my g is 9.8. So I guess I'll multiply by 9.8 on both sides. And I'll divide by sine of 60. And that will give me V naught squared. And then just take the square root of that, and that should give it to us. Let's pop it in to see what we get. Turn it on our trusty calculator. If I take a 9.8 times 100, divide it by the sine of 60, okay, I get 1131. So V naught's going to be the square root of 1131 and change. I'm going to say take the square root of, and notice I'm just going to hit my little arrow going up till I get that number, hit enter to pull it down, close the parentheses, and what is the square root of that number? About 33.6. 33.6, and that's in meters per second. So that one was much easier. Some of them are easy, some are not. Okay, one more, and then we just have to talk about something, and then we'll be finished for the day. A gun is fired with an angle of elevation of 30 degrees. What is the muzzle speed if the maximum height of the shell is 500 meters? So what's happening here is you're launching something at 30 degrees. You don't know what V naught is. It goes up and it goes down. And I know the maximum height is 500 meters. And they want us to find V naught. Any suggestions? Well, what do you think we can do to do that one? Well, I say at the top, what do I know? I know at the top, y is 500 meters at the top. Right? At the top, y is 500 meters. What else do I know at the top? I know my velocity in the y direction is 0. Because remember, the velocity in the y direction is y prime. That's how much y is changing. Here, y is increasing, so y prime's positive. This side, y prime's negative. So at the very top, y prime is 0, because y prime is in between increasing and decreasing. So, so if the velocity in the y direction is 0, I'm going to look here and I'm saying, at the top, Vy is 0. So I have minus gt plus V naught sine, and my alpha was what? 30 degrees, was it? Sine of 30 degrees is 0. The time that I'm at the top, this is 0. We could solve for t here, couldn't we? I would get V naught sine 30 equals gt. or t, is v naught sine 30 over 9.8. Okay, that's the time at the top, the time that I'm at the top. But I also know at the top what my height is, right? My height at the top was 500, right? So taking that equation, if I take this time, which I'm going to rewrite, t was v naught sine 30 over 9.8. Do you mind if I write out what that is? What is sine 30 is a half. So if I just multiply by 2 over 2, that would be v naught over what, 19.6? Is that okay? Just to simplify it a little bit. If I take that time and plug it into that equation, I'd get y is equal to v naught sine of 30 degrees times t, which is v naught over 19.6, minus 1/2 g, which is 9.8, times t squared, which is v naught squared over 19.6 squared. Okay, now that looks sort of dreadful. Okay, but let's see. Y is equal to v naught squared times sine of 30 over 19.6 minus 1/2 times 9.8 over 19.6 squared times v naught squared. You with me? But this is the time that I'm at the top, so I know that this is equal to 500. Okay? Well, if you notice on the left, why don't we just factor out the v naught squared times this awful mess? Let's find out what this number is right here, because it's going to be sine of 30 over 19.6 minus 1/2 times 9.8 over 19.6 squared. Let's see what that turns out to be. Okay, so popping that in, let's see what we get. We get sine of 30 divided by 19.6 minus 1/2, which is 0.5, times 9.8 divided by 19.6 squared, unless I made a mistake. And I get, what do I get there? 0.012775? 12755 is equal to 500. And so therefore, v naught squared would be 500 over that number. So I'm going to take that number 500, and I'm going to divide by, and when I divide by, I want to pull that number up using my arrow key. I'd like them to pull it up on the screen so I can see it, because I have a blank thing. Is that highlighting the number that I just pulled up? The 0.01277? There you go. Hit enter. Take the enter of that, and we have, what is that? 39200. So v naught is the square root of that, and if I want to take the square root of, pull that number back down, close parentheses, I get 197.98, which I think I will write as 198 meters per second. So that one probably was the hardest one that we did. And let's see, very good. I got the same answer that I had before, so that's good. But what did I do? Let's just talk real quick. What did I do? I look, each time you do any of these kind of problems, you have to ask yourself, what do I know? This is going up and down. At the top, I know Vy is 0, and I knew y was 500. So using that, I could find the time, I could write the time in terms of the V naught and then plug it into the other one. Now what I'm doing lastly, I just want you to sit back and enjoy the show. All right? Really, just take a couple minutes and let's talk. We're not going to be doing this a whole lot, but if those of you that go on and take advanced physics courses, you're going to see this a lot. In physics, you can have a particle moving along a curve like this, all right? Or you could have the sun. Here's your sun, and you're moving along some orbit, all right? In physics, what they love to do when they have an object moving along a curve, they like to talk about your acceleration that's in the direction of the unit tangent And they also like to talk about the part of the acceleration that is in the direction of the unit normal. All right, now I just want to show you the derivation real quick. But we're talking about writing your acceleration in terms of the tangent vector and the unit normal vector, instead of in terms of I and j and k like we did. Now notice, just reviewing, k, when we did curvature last time, it was the magnitude of t prime over ds dt, which is equal to this. Notice, if I multiply through by v on both sides, I get the magnitude of t prime is equal to your curvature times your velocity. Don't copy this down because I'm not going to test you on it. Okay? Now, taking that, remember the magnitude of t prime, is the magnitude of t prime times the unit vector in its direction, which is n. All right? So I could say t prime is equal to kv times the unit normal. All right? Now taking that, lastly, tangent is equal to the r prime, the definition was r prime over its magnitude. R prime is v, magnitude of r prime is little v without the arrow on it. So if I multiply by v on both sides, I get v equals v times t. All right, now taking v equals v times t, I'm going to differentiate both sides with this. Now if I differentiate both sides, I get acceleration. But this is a product, so you've got to take the derivative of the first times the second, plus the first times the derivative of the second. And then, here, I have my acceleration equals, I have v prime times t, v, and I'm going to replace this t prime right here with what we derived just a few minutes ago. T prime is equal to kv times the unit normal, so I replace that there. So this gives me acceleration is equal to v prime times the tangent vector plus kv squared times the unit normal. This is my acceleration. Now, why is this, what's so cool about this? All right, now let me just talk for a second, even though we're not going to be doing a whole lot with this. A lot of physics books like to write your acceleration as this v prime t plus kv squared n. This is your acceleration in the direction of the unit tangent vector. This is what's called your normal component. Now what happens is, so you can represent your acceleration in the tangent direction as v prime, and the acceleration in the normal direction is kv squared over n. A sub t times t gives you this much, and this gives you this much, and the two added together equal your true acceleration. The reason physicists are so excited about this is when you have an object either moving along a circle or moving along a sphere, if you break your acceleration up into the part that's in the direction of the tangent and the part that's normal, the part that's in the direction of the tangent is the one that increases and decreases your speed. You see, it's v prime, how your speed is changing. This piece has nothing to do with increasing and decreasing how fast you're going. This part is changing your direction. Okay, changing your direction. I'm sure some of you took physics courses, and you might remember when you were doing gravitation, or you were doing centripetal motion, and you probably had your instructor tell you acceleration due to gravity when you have centripetal motion, when you're going around something, was v squared over r. And they never proved it, but you're like, how did they come up with something so weird as that? V squared over r. How did they do that? Notice, this is your acceleration in the normal direction. Notice, if you've got a circle and you're going around a circle, here's your object. Your force is going in that direction, your normal force, right? Remember, curvature for a circle was 1 over r. We just derived it. The acceleration in the normal direction is v squared over r. If you're going. Now I just wanted to mention it because I know some people that take the Calculus 3 are going to go on and you will use these type of things. We don't have time to do a whole lot of depth. You'll notice in your homework you just watched 5 minutes of tape, and none of that's going to be in your homework, so you don't have to worry about it. But I just want you to be exposed to it in case you ever go on to courses where you might need it. For the rest of us, between now and next time, I want you to read pages 902 to the top of page 911. I'm having you stop where they're talking about the component of the tangent, the acceleration in the tangent direction and the normal direction. These are your exercises, and these are the review exercises. Now for you people at home, we do not have a review section. It's up to you that are watching the videotapes to go back and study your notes and to get ready for the test. It's very important for you to do all the homework. It's very important for you to look at the chapter review and then also look at the practice test that I have posted for you. If you have any questions, those of you that are in the class, you can come see me anytime. Those of you that are at home, take the time to give me a call. Email me, fax me. Those of us that are local in Newcastle County, you're more than welcome to come up and see me during office hours. All right, so those at home, good luck on your test. All right, and I'll see you next time.